Welcome to the session on functions and graphs, functions and mappings. The objectives for this session are to understand mappings and functions and use domain and range. A mapping will transform one set of numbers into a different set of numbers. It can be described in words or via an algebraic equation. It can also be represented as a graph. A mapping is a function if every input has a distinct output. Types of functions are one-to-one or many-to-one. Let's have a look at some illustrations. We're going to first look at a one-to-one function. So suppose we have a set A and a set B. Each value in set A is mapped onto a value in set B, as shown. This is a one-to-one function. Let's now take a look at an example of a many-to-one function. We have a few values in A, this time mapping to one value in B, as shown here. This is a many-to-one function. We may have another scenario. So in this scenario, we may have one value in the set A mapping to two values in the set B. This is one-to-many, but it is not a function. For a mapping, the domain is the set of all possible inputs, and the range is the set of all possible outputs. Some mappings can be made into functions by changing the domain. For example, y equals root x. Here's a sketch of y equals root x. If the domain is the real numbers r, then y equals root x would not be a function, as values of x less than 0 cannot be mapped anywhere. So, for example, square root of minus 4 in the real plane does not go anywhere. So, if we redefine f of x as f of x equals root x for x in the real numbers and x greater than or equal to 0, this will now become a function. We can equivalently write f such that x goes to or is mapped to root x, where x is a member of the real numbers and x is greater than or equal to 0. Let's now take a look at an example. Pause the video and have a go. Press play when you're ready to view the solutions. So in this example, we're required to state whether this mapping shown on your screen is one-to-one, many-to-one, or one-to-many. We're also required to state whether it is a function or not. So let's have a go at part A first. Is this mapping one-to-one, many-to-one, or one-to-many? Out of the three illustrations we can see towards the top of our screen, the one on the right fits the bill best. We have one value mapping to two values. Therefore, this is a one-to-many mapping and it's not a function. And now for another example. Again, for this example, y equals 3x minus 2, we're required to state whether this mapping is one-to-one, many-to-one, or one-to-many, and also state whether it's a function or not. Pause the video and have a go. Press play when you're ready to view the solutions. So let's solve this. Is this mapping one-to-one, many-to-one, or one-to-many? If we take a look at the graph, we can see that each value of x is mapping to a single value of y. Therefore, the mapping is one-to-one. Now let's take a look at whether this mapping is a function or not. Remember that a mapping is a function if every input has a distinct output. This is indeed the case for this example. Therefore, the mapping is a function. Now let's take a look at another example. Pause the video and have a go. Press play when you're ready to view the solutions. So again, we're required to state whether this mapping is one-to-one, many-to-one, or one-to-many, and also state whether this mapping is a function. So let's solve part A first. What is this type of mapping in particular? Notice that each value of x is mapped to one value of y. Therefore, the mapping is one-to-one. Now let's solve part B. We are required to state whether this mapping is a function. Let's again recall the definition of a function. A mapping is a function if every input has a distinct output. However, if we consider 0, we know that it's not mapped anywhere because 2 over x or 2 over 0 does not make sense. Therefore, the mapping is not a function. We can omit 0 in order to make a function. So we can define f of x as f of x equals 2 over x for x in the real numbers and x not equal to 0. Now for another example. Again, for this function y equals x squared minus 2, we are required to state whether this mapping is one-to-one, many-to-one, or one-to-many. We are also required to state whether this mapping is a function. Pause the video and have a go. Press play when you're ready to view the solutions. So let's solve part A first. This example seems to fit the second illustration. Take a look at the diagram for y equals x squared minus 2. Notice that x, for example, maps onto y, but minus x also maps onto y, because x squared and minus x all squared are both the same. So in other words, both x and minus x are mapped to one y value, and therefore this mapping is many-to-one. And now for part B. Is this mapping a function? Again, referring to the definition of a function, a mapping is a function if every input has a distinct output. Therefore, the mapping is a function because each value in the real numbers is mapped onto another value in the real numbers. Now let's take a look at another example. Pause the video and have a go. Press play when you're ready to view the solutions. Let's solve example 5a first. We are required to find the range of f of x equals 4x minus 5 for the domain x equals 2, 3, 4, and 5. We are also required to state if the function is one-to-one or many-to-one. So let's solve this. So let's solve part A first. We are required to find the range of f of x equals 4x minus 5 for the domain x equals 2, 3, 4, and 5. So let's see where each of these values map onto. 2 maps to 3 because 4 times 2 minus 5 is equal to 3. 3 maps to 7 because 4 times 3 minus 5 is 7. The value 4 maps to 11, and the value 5 maps to 15. Therefore, the range of f of x is 3, 7, 11, and 15. And of course, f of x is 1 to 1. Now let's take a look at part B. We are required to find the range of g of x equals 2x squared for the domain x in the real numbers and x greater than or equal to minus 3 and less than or equal to 3. We are also required to state if the function is 1 to 1 or many to 1. So let's solve this. Here's a sketch of y equals 2x squared. We of course have x in the real numbers and x between minus 3 and 3. The value 3, as shown in the graph, is mapped to the same value that minus 3 is mapped to. And this value is 18. 2 times 3 is 18, and also 2 times minus 3 is also 18. Therefore, the range of g of x, as we can see from the diagram, is g of x greater than or equal to 0, but less than or equal to 18. And of course, g of x is many to 1 because we have, for example, in this diagram, as you can see, two values mapping to 1. And that's the case for several values. And now for part C. We are required to find the range of h of x equals 2 over x for the domain x in the real numbers and x greater than 0 but less than or equal to 4. Here's a sketch of h of x. Notice that the minimum occurs at h of 4, which is equal to 2 over 4, which is equal to 1 over 2. The value x equals 4 is mapped to a half. Also, as x tends to 0, h of x gets larger and larger. In fact, it's tending to infinity. Therefore, if we want to find the range of h of x, we would state it as follows. The range of h of x is a half less than or equal to h of x. And of course, h of x is 1 to 1. And now for example 6. Pause the video and have a go. Press play when you're ready to view the solutions. Let's take a look at part A first. The function f of x is defined by f such that x is mapped to 3 minus 2x if x is less than 1 and x squared plus 2 if x is greater than or equal to 1. We are required to sketch y equals f of x and also state the range of f of x. So let's solve this. Here's our sketch. This part is y equals 3 minus 2x, where x is less than 1. And this part is y equals x squared plus 2, where x is greater than or equal to 1. 1 is mapped to 3. Also, although there is a jump, the function is still defined for all x. Also, notice that f of 1 lies on the quadratic curve, so we use a solid dot here. And we use an open dot on the line as shown. Note also that f of x does not equal 1 at x equals 1. So f of 1 is greater than 1, not f of 1 is greater than or equal to 1. And therefore the range is the set of values that y takes, and also we have that f of x is greater than 1. Now let's solve part B. We are required to solve f of x equals 11. So let's solve this. Here's our curve, or here's our function. Here's y equals 11. If we want to solve f of x equals 11, how do we find our solutions? On the positive side, or when x is greater than or equal to 1, or on the negative side, when x is less than 1. Notice that on this positive side, or on the side where x is greater than or equal to 1, we have one solution. So the positive solution is where x squared plus 2 equals 11. And solving this gives us x equals plus or minus 3, but of course we know that the solution is positive, and therefore x is 3. On the negative side, or the x is less than 1 side, we have one solution also. So the negative solution is where 3 minus 2x equals 11, because for x less than 1, we have this linear equality holding. And solving for x gives us x equals minus 4. And so we have two solutions, x equals 3 and x equals minus 4. This brings us to the end of this session. If you have understood its contents, you should be able to understand mappings and functions and use domain and range. Thank you very much for listening. To understand this topic in greater depth, do attempt the exercises in your textbook related to it.